So here's another thing we didn't quite finish. I talked about bloom filters, and I said I would do something geographic with it, but we haven't yet. Let me start by summarizing kind of where we end up with bloom filters, and I'll give you a quote by Broder and Mitzenmacher, who did important work for bloom filters. Wherever there is a list or set, and space is at a premium, consider using a bloom filter if the effects of false positives can be mitigated. So if you can organize that false positives aren't really a problem. Okay, so let's do GloBiMaps. I think it stands for global scale bitmaps, I guess. We're not going to do the entire analysis because you already know what bloom filters are, and this gets to be a little bit technical, but let's look at what it does on the main data set that they use in the paper, which is so-called global urban footprint data set. So this is basically a pixel is black if there is a building, and it is white if there is not a building. Of course, this is now a 2D bitmap, so there's some kind of projection behind this, but we're not going to care about that. And what is the resolution of this dataset that covers the entire world? Well, it's about 3 million by 2 million pixels, and not every pixel covers the same land area. Because of the projection, but on average, we're talking about 90 square meters per pixel, and only about 1 in 1,000 pixels is black. If we would store this entire bitmap with just 1 bit per pixel, so that's the bit set way of storing it, as I talked about it last time, this is 600 and something gigabytes stored. But of course, the entropy is much lower because most of these pixels are whites. Now, there are lots of things that you could do with this. Let's try to think of ways to store this with fewer bits. Well, one way that you could do it is you could store it as a JPEG. That sounds like a bad idea. That's lossy. It's only 1 bit. It's black and white, so maybe you can use a GIF or a GIF, depending on how you pronounce that. And then there are a bunch of details about how the file format works precisely and if you can actually fit this many pixels in a single file. But the basic idea there, that if you look at this picture, also makes sense, is you could do so-called run length encoding. So rather than saying this pixel is black, this pixel is white, 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 etc. You get the idea. The way you could store it is, okay, there's 1 black pixel, and now there are 1,274 white pixels, and then now you need to store this number, but the number of bits you need to store a number is logarithmic in the number itself. So you save information there, and in the Atlantic Ocean there are no buildings, so you save a lot of space on all of these white pixels. Another way you could do it is you could say, okay, I assume that everything is white, and I store a list of the black pixels. That was the very first way that we talked about when we talked about set membership data structures. Both the run length encoding and storing the black pixels as a list have the following problem. If I come along and ask about a particular pixel, is this pixel black or not? Then in case of the run length encoding, I need to decode this in some way to figure this out in the list. Well, maybe it's sorted or it's a tree like we talked about, and then it's logarithmic time. But I don't have a constant time way to check a particular pixel. Maybe that's not the most crucial use case, and we're going to get into use cases in a second, but just as an observation, this data is not that hard to compress. Most of it's white, and then there's a bunch of black pixels, but the ways to compress that are not well suited to decoding and answering the question, this random pixel, is it black or not? So let's see how we could use a bloom filter here. And the idea is extremely simple. We just put the black pixels in the filter as a set membership data structure. So my universe is all possible pixels that could be black. So it's the entire image. This is the millions by millions of pixels. And if I would store it in a bit set, we were talking about this 600 and something gigabyte bit set. But now let's store it in a bloom filter, and then let's say my globe is 6 by 6 pixels, and here what I've drawn is the black pixels are the actual black pixels and the white pixels are white pixels. But if you remember, a bloom filter has false positives, so I also end up with, I've drawn 4 of them here, but there are some false positives. So how does this affect how we are going to use a GloBiMap? millions of pixels by millions of pixels image is probably hard to look at. If your display is only like 2000 by 1000 pixels, then I'm very zoomed in. So what I'm going to do with this map is probably I'm going to have to zoom out. And how does that work? Well, if I have this 6 by 6 image, now I want to show it on a 2 by 2 monitor. These are of course ridiculous numbers, but like if I have a millions by millions image and I want to look at it at a 2000 by 1000 image, but in our example 2 by 2, then the way you do that is the input may be black and white, but we're going to render a grayscale image. So what should I do with my 4 pixels? Well, these 2 by 2 pixels should probably be the average of pixels in here. So my top left pixel should probably be brightness 1, 2, 3, 4, 5, 6 out of 9. Should probably be brightness 2/3. Well, we are a bloom filter, so we have some false positives here too. So that would probably be a 5 out of 9, and we'll see what happens there. But another way to render it is to just look at individual pixels. So if in each of these 3 by 3 parts, I just look at the top left. So then I would get this one is white, this one is, it's wrong, but this one is black, and this one is really black, and this one is also a false positive. So then I would have this picture as a small representation of this one. If instead I look at this pixel over here, then I would have this one, and then if I look at the third one, then I get an entirely empty image, which is of course also a little bit silly. So this is not really a good way to scale down, and like I said, what we should probably do is take the average. This is going to take time, and I'll get into that, but let's say what I just do is for every pixel here, I loop over all pixels in the full resolution and I see if they're black or not, and then I take the average. So if I do that, then I get this pixel. Among these 9 pixels, 4 of them are black. Among these pixels, 6 of them are black, etc. And I get this image. But there's something wrong with this image. I mean, these are actually the averages I get from this bloom filter, but how is this wrong? Well, there are errors. What do these errors do? They turn white pixels into black pixels. So on expectation, this image is going to be a little bit too dark. And in fact, we have an expectation for how much darker we think it is than that it should be, because we have this bloom filter. We know everything about it. We have the hash functions. We have the size. So we know the false positive rate. I've drawn it in such a way that I have about 1 false positive per 9 pixels over here. So in this very simplified example, what is much closer is I should subtract the expected false positives from each pixel. And then, now this number still isn't correct. There were no false positives here, and I subtract 1, so now I see 2. And this one still isn't entirely correct. But on average, on expectation, I mean, of course, in the real world, you don't do this for just 4 pixels. So that you get, in expectation, correct averages here. So I thought that was a cool idea that you can also keep in mind. If you're doing statistics on your bloom filters, you actually have a pretty well concentrated expectation on how many false positives you get. In terms of rendering, this, of course, is still pretty slow because for every pixel that I render here or render here, I have to look at 9 over here. And so if this is millions by millions and this is 2000 by 1000, I'm still looking at all of these pixels, and maybe I should just have stored the bitmap or the list of pixels or the run length encoding if I'm just going to look at everything anyway. That's kind of annoying. So let's fix that. Taking these averages is slow. Can we save ourselves some time here? I mean, I like some amount of grayscale, but I don't need numbers more precise than 1 in 265 is is not something that I can even communicate to normal monitors. Well, I guess we have a high dynamic range these days, but even 8 bits of grayscale precision is not something that you can easily see. I would also, I think, be pretty happy with this just going to 9 or maybe 16 if I just look at 4x4 smaller pixels. So if taking averages over large areas is expensive, let's not do it. And then what we can just do is make the universe even larger. And instead of just putting X, Y pairs in the Bloom filter, I put triples in the Bloom filter. X, Y, and a zoom level. Now I can only store yes or no in the Bloom filter. This is binary. I can't put the average in this area is such and so. I can just maybe threshold it or just take the disjunction. So is there anything in this area? And then I can, for a certain pixel, pick a zoom level below that so that I can maybe take 9 or 16 samples and take the average of that. And then the random access property of our Bloom filter is good again. I can just look at this all over the place, and I just need to make it a little bit larger and maybe get one more hash function, because what I'm doing here, if I do this zoom levels, if I do those by factors of 2, then this only doubles the number of items in my set. So this is actually pretty cheap in terms of space, time, and error rate. But let's actually look at sizes and error rates and hash functions at this point. So if we have this global urban footprint dataset, and we have this 3 million by 2 million pixels, which would have been 600 gigabytes as a bitmap. Now in the paper, they look at 3 different ways to store this. So the number of pixels, I didn't list it on the slide here, but it's like 1/1000th of this is fixed. So as we talked about last time, it may kind of seem weird to analyze something where n, the number of items, is fixed, but that's precisely the situation that we have here. We have this particular data set that we want to store and be able to query. So the thing that we're going to vary here is the size. We're going to pick 8 gigabytes, 16, or 32. And so then we have the number of bits and we have n, so we can optimize k to give us the best possible false positive rate, which is, in these cases, almost 1% or 10 to the minus 5 or even 10 to the minus 9. And at this point, I'd like to introduce you to one more idea that I think is really fun. So we have this urban footprint data. As a bitmap, it's 600 gigabytes. We can store it as a Bloom filter of 8 gigabytes. And then we have a false positive rate of almost 1%. And this is going to be terrible because this false positive rate is much higher than the actual positive rate. On the face of it, this is a fairly useless data structure. But I can look at the entire thing, query each pixel, and then there's no randomness at this point. So each pixel is either true negative, actually white, false positive, or true positive. And I could, it's going to take some time, but I could look at all of the pixels and see if they are false positive. And then all of these false positives, I could store them in, let's say, a hash set or a list or whatever. I could put them into some kind of other set membership data structure without errors. So how big would this data structure be that has all of the false positives? So then my real query is look at the Bloom filter. And if the Bloom filter says yes, then I look at my error correction table, my big set of false positives, and I check, was this actually false positive? And if it's in there, then I actually say no. And if it's not in there, then I know that this is a true positive, and I say yes. So how big is this set if I throw this in a list? Well, unfortunately, I don't know. How big is it? It's about 300 gigabytes. So this is actually smaller than storing the bit set, because this is 307 gigabytes plus 8 gigabytes is less than 611 gigabytes. And the false positive rate for this combined data structure, 8 gigabytes of Bloom filter, 300 gigabytes of error correction, is 0. This is a correct and deterministic data structure. But really, it's not that convincing anymore, because what we said was we don't really want to store a normal set data structure because we want this random access to be quick. So that's a bit of a shame because I have this almost 1% error probability on my tiny fraction of true positives. So I'm going to be checking false positives a lot of the time, and there are a lot of them. So I'm going to have to look at that, and it's going to take time, and it's going to be kind of sad. But maybe this trade-off gets better. What happens if we do the same thing with the 16 gigabyte Bloom filter? Then we need more hash functions, and then we get a lower false positive rate. And so there are fewer false positives. And indeed, what we see is that we can store all false positives of this 16 gigabyte Bloom filter in 2.5 megabytes. So this is much smaller all of a sudden, and this is the power of exponentials and logarithms in there, because we have this exponentially vanishing error probability by increasing the size. So in 16 gigabytes of Bloom filter plus 2.5 megabytes of error correction list, we have a perfect data structure that almost all of the time we can query in constant time, because the Bloom filter just says no. Or if it says yes, we need to have a quick look in 2 megabytes of error correction lists. So, I mean, this is very small and it probably fits in the cache. This is going to be great. What happens if we make the large Bloom filter? Then the false positive rate really goes down and we hardly have any errors at all anymore. Actually, we can store them in about 140 kilobytes. Maybe we can binary search this, or maybe even do a linear search. If it's in cache, maybe this is going to be super fast. But the trade-off is a little bit like, this is now larger. 16 gigabytes plus 2 megabytes is less than 32 gigabytes plus almost nothing. So in terms of storage, this medium one is actually the better trade-off than the small Bloom filter or the large Bloom filter. So that's kind of interesting that there's this curve in there somehow where this false positive rate influences the error correction table so significantly. And depending on your computer architecture, I mean, it's much nicer to look in this really small error correction table rather than this larger one. But now you're also looking at a larger Bloom filter. So maybe this is based on caching or how much RAM you have. There could be interesting trade-offs there, and you would really need to do experiments on your real hardware to see how that turns out. But yeah, I thought it was quite cool to actually store this error correction table and fix it in that way. So that's what I wanted to say about GloBiMaps.